Hello?
Good morning. My name is Adam Smith, calling from nobelprize.org, the website of the Nobel Prize in Stockholm.
Yeah, very good. I already talked with your colleagues this morning.
Well, first of all, congratulations on the award of the
Well,
Nobel
thank you.
Prize. It must be very special in particular because you came up with the idea of this detector.
Well, be careful with that. Other people also had thought of detectors. Don't be careful with that. I mean, in fact, there was a group in Russia in 1962, Gerstenstein and Pusovit. I can't pronounce it for you well. They wrote a little paper in a Russian journal, which none of us knew about, that not to do it by interferometry so much, but to use light as a way of doing this. And then it turns out Joe Weber, which had unbeknownst to us, but also Joe Weber, who was sort of the first person to start thinking about this.
With his Weber bars.
The Weber bar, but at the end of the Weber bars, he also has some notes about that. Maybe we should do this with interferometry. The whole world tried to reproduce the Weber experiments. I don't know if you're probably too young to know that, but the thing is that in Weber made his big announcement in '69, and where he showed that he had, in 3 bars, he had seen gravitational waves, and then that got virtually everybody in many groups, both in Europe and Asia and in the United States, tried to reproduce this, and to everybody's disappointment, nobody saw the same thing that Joe Weber did. And the way it happened in my life is I was teaching a course in general relativity in the middle of that epoch, in sort of 1967, and I couldn't explain the way a Weber bar worked, mostly because I just didn't know enough, okay? But it was that I thought that there would be an easier way to explain how a gravitational wave interacts with matter if one just looked at the most primitive thing of all, 3D floating masses out in space, and look at how the space between them changed because of a gravitational wave coming between them. And I gave that as a problem in the course, and the kids in this course did it because it's a fairly straightforward calculation. And that was sort of 67, and by about 72 or 71, it turned out that many people were not seeing, it was already quite clear that the bar to technique and Weber's experiments were not being seen by others. And so I spent a summer thinking about maybe this idea that I gave as an exercise in a course would be a nice way to try to do this because it was so easy to understand it. And that then turned into LIGO, but other people had thought of it. I didn't know that.
Nevertheless, a journey from the early 70s to now, the sense of achievement and excitement.
Oh, no doubt. Look, the thing, it has nothing to do with pride. It has to do with, I did something which others didn't do. I actually did a calculation of what might be all the things that get in the way of being able to do it, which actually turned out to be very useful. The different noises that would make it impossible to see it, or possible to see it. You had to solve a whole set of problems. And that was my contribution to it in the early days.
Well, that's it. It's quite mind-boggling to think of how precise this piece of equipment is.
Yeah, that's true. And that's what took, by the way. I think the easiest way to say it is that the concept is very straightforward. You measure the time it takes light to go between 2 orthogonal directions in the gravitational wave. And you measure that time very carefully. And that idea is sort of trivial. Most people who know a little bit of physics can make that calculation. On the other hand, what happens to make it actually happen, because the sizes of things are so small, and I think the easiest way to say it, are you familiar with exponential notation? Can I use that?
You can, yes.
Yeah. Well, okay. I think the best way of saying it is this way. There are 2 factors of 10 to the 12 that had to be solved. One of them was that the light wavelength itself is 10 to the minus 6 meters. And so you had to devise a way to make light, which has this wavelength of 10 to the minus 6, to be good enough so you could measure 10 to the minus 18 meters. And that is a factor of 10 to the 12. And that was not the hardest problem, but that was one of the major problems between, let's say, 1972 to 2015. But the other one is another factor of 10 to the 12, which is just as serious, and that's much harder to solve. And that took longer. And that took more effort. And that was that even though you may have this wonderful method of now breaking up a light fringe so you can do a part in 10 to the 12 of it, you still don't know that the thing that you're measuring is not being pushed around by forces that make it move much, much more, that are not gravitational, that are not gravitational waves, but other forces like thermal noise or seismic motion or God knows all the different things that happen in the world that you are not being, that same mirror that you're looking at is not being pushed around by things that make it move more than 10 to the minus 18 meters. And that is another factor of 10 to the 12 about, because it turns out the ground motion is about a few microns, 10 to the minus 6 meters again. So you have to devise a wonderful way to get rid of the ground motion and then get rid of the thermal noise. And now it's really at the point where we're worrying about the quantum noise. So, but it was all pretty well organized. I mean, in the sense that people knew what the problems would be. It's just a matter, it takes time to do a thing like that.
The contrast between the minute precision to make the measurement and the size of the actual gravitational wave. Which is
yeah. It's really. What it tells you is something really interesting. It tells you that space is very, very stiff to distortion. The Einstein waves can be thought of as a distortion of space and time. But the way we see it as a distortion of space. And space is enormously stiff. You can't squish it. You can't change its dimensions so easily. And it turns out that I think the easiest way to see that, or say it, is that if I'll give you an example so that you can use it or think about it. If you put this whole thing that was detected, back at the first detection, and put it not at a billion light years away, but rather put it at the sun, the distance of the sun. Suppose the sun had somehow put out those gravitational waves. You would have had a motion at the Earth of, a motion over a kilometer of about only 10 to the minus 6, only 10 to the minus 6 meters. It's still tiny.
Yes.
And in fact, you could just about hear it in your ear. But the amount of power that went to you through you is something like 10 to the 24 watts per centimeter squared. It's huge. In other words, the sun puts out about 10 to the 4 watts.
So you can translate that into what the?
Yeah. In fact, almost all we did translate that in that initial paper into the amount of power was sort of brighter than anything in the universe, but 50 times brighter for the few moments in which that gravitational wave was actually traveling through you. It's an enormously stiff. The system just does not like to make. You can't distort space very much, but you do get a little bit, and that's what we measure.
That is a really beautiful concept to mention on this call. Thank you so much. We will hopefully discuss all these things more when you come to Stockholm. You will be coming to Stockholm in December.
Of course I will, yeah. And I intend that if you can manage it, I would like to, and I prefer really often to talk to high school students.
Yeah.
I mean, mostly because I think they're the future for us. And so if I know I have to give lectures, I'm very happy to do that, and so are my colleagues. But if you think that there are some high school students who would benefit from understanding this a little better, I'd be very happy to do that.
We will most certainly work to fill rooms with high school students for you.
Yeah.
That's a great objective. We very, very much look forward to welcome you to Stockholm. How do you feel about the coming day, which will be completely taken over by this?
But today?
Yeah.
Yeah, I don't know. I'm at home. I'm still not completely dressed. I am now, a little, but yes, I know that I have to confront all my colleagues, and it's a charming thing to do. It's just a little awkward, that's all. Yeah.
Good luck with finishing getting dressed, and we look forward to meeting you in Stockholm in December.
Yeah, I'm very happy to come. I've been there once with, you gave a Nobel Prize to one of my colleagues, named John Mather and George Smoot.
Of course, because you also worked on the Kobe project.
Yeah, I worked on that with them, and I've been there, and it's really quite a pleasure to come there. So.
Good. Okay, well, we greatly look forward to meeting you. Thank you so much.
Yeah, bye-bye.